Okay, in this video we're going to be taking a look at harmonic oscillators. Before I do that, I want to just talk briefly about how I could test you on the trace determinant plane. I won't ask you to draw the trace determinant plane and draw a representative phase portrait for every possible region. That's just too much. But I could give you a point and say, draw a representative phase portrait for a system that would be plotted there in the trace determinant plane. I could give you a specific matrix or simply tell you its trace and determinant, ask you to plot that in the trace determinant plane, and draw a representative phase portrait. I could ask you if there's more than one possibility. For example, when we have a repeated eigenvalue, and I don't know how many eigenvectors I have, I could ask you to draw both possibilities. I could ask you what the equation for this parabola is. I would not suggest that you memorize it. I would simply remember that if you write out your characteristic equation and then you solve for your eigenvalues using the quadratic formula, this equation corresponds to what makes the discriminant, the quantity under the radical, equal to 0, because that's going to be the boundary then between having a negative number, which gives us complex eigenvalues, and having a positive number under the radical, which gives us real numbers. Okay, so now I want to tie this all in with our harmonic oscillators. So remember, if I have a harmonic oscillator, this is the general way the system would look. M is the mass, so it's positive. K is the spring constant, so it's positive. And B is either 0 if it's undamped, or it's positive because it's the damping coefficient. So if I take a look here, my characteristic equation will be lambda squared minus the trace. So the trace is 0 minus b over m, so the opposite of that would be plus b over m times lambda, plus the determinant, which is 0 minus a negative k over m, so plus k over m is equal to 0. Now, if I solve for lambda, that's going to be the opposite of b over m, plus or minus the square root of b squared over m squared minus 4 times 1 times k over m all over 2. To simplify this, I'm going to just do a couple of things. First of all, I'm going to break it into two parts and distribute the 2. So I'll have negative b over 2m plus or minus this lovely square root over 2. But I'm going to just get a common denominator for what's under the root here. So that'll become b squared minus 4km over m squared. And then I can say, well, the square root of m squared, that's the absolute value of m, which is just m because m is bigger than 0. It's the mass. Okay. So I can pull out an m here and I can just bump that to the bottom. So I get negative b over 2m plus or minus the square root of b squared minus 4km all over 2m. All right. So I want to just take a look at the different types of harmonic oscillators we can have, what that makes the trace and determinant, and where they end up on the trace determinant plane. So if b is equal to 0, that was our undamped harmonic oscillator. And remember, that meant that our phase portrait was going to give us this situation where the origin was a center. Because if it's undamped, there's no friction or air resistance. It's just going to be oscillating back and forth, and there's nothing to slow it down or change the magnitude of those oscillations. Okay. Now, if I take a look, if b is equal to 0, that's going to mean that the trace is 0, because now this is 0, so 0 plus 0 is 0. The determinant, 0 minus a negative k over m, is k over m, which is positive. So t is 0, d is positive, that puts us somewhere here. And if we look back at our previous work, that does actually correspond to where we were going to have a center. Excellent. Now, all of the other possibilities involve b being positive. So if b is going to be bigger than 0, then the trace will always just be negative b over m, and the determinant will still be k over m. So negative b over m is negative, k over m is positive. So we're always going to be somewhere over here in quadrant 2. So the trace is negative, the determinant is positive. Okay. Now what I want to do is compare the condition for being here, here, and here, because these are the three possible places we could be if we're in quadrant 2, with the criteria we had for when we had something that was underdamped, overdamped, and critically damped. Okay. So, I know that here, my criterion for whether it's going to be overdamped, underdamped, or critically damped is going to be determined by the sign of this. If this is a negative number, that's going to give me imaginary stuff. That's going to give me something that's underdamped because I'm going to have a spiral sink. I'm still going to have oscillations, they're just going to be shrinking and getting slower. If this is 0, we have something that's critically damped. That would mean that we would have a repeated eigenvalue, and so we'd have that wanting to oscillate but can't quite do it. Okay, and then if this is positive, we would have 2 real eigenvalues, and so we would just have a sink, and we would have no oscillations going on at all. There's no rotation around there's no even attempt to rotate around the origin. Okay, so I want to compare that criterion with what we have here. Remember, in general, it's lambda squared minus t lambda plus d equals 0. So lambda is equal to t plus or minus the square root of t squared minus 4d all over 2. So here, the criterion for where we're going to be is t squared minus 4d. I want to just show you that that's equivalent to this. Remember, we said if b is positive, the trace is going to be negative b over m, and the determinant is going to be k over m. So if I just take a look then at what t squared minus 4d becomes, that becomes b squared over m squared minus 4k over m, getting a common denominator, that's b squared minus 4km over m squared. I know the m squared is always going to be positive. What determines the sign is still that b squared minus 4km, which is kind of cool. Okay, so essentially this was our undamped harmonic oscillator. Here, where I've got complex roots, I've got a spiral sink, this is going to be our underdamped. This is going to be our overdamped. And then on that parabola, that's where we would have something that is critically damped. Pretty neat to see the pieces coming together.